In this final mini-lecture on the nucleophilic substitution of alkyl halides, we'll take a look at ways of making alcohols into good substrates for the nucleophilic substitution reaction, and ways for making nucleophiles out of species which are not nucleophiles. So in the previous mini-lecture we said that a hydroxide group, an OH-, is a lousy leaving group. For that reason, alcohols are poor substrates for the SN2 reaction. In order for a nucleophile to attack an alcohol, we would have to lose OH-. An OH- being a strong base is going to be a very poor leaving group. As a result, alcohol solvents don't react with nucleophiles. We do have several ways, though, that we can make alcohols into good substrates for a substitution reaction. One approach is make the OH group into something that will fall off a bit easier. We're going to see two examples of ways to make the OH group into a better leaving group. A second approach is to simply replace the OH group altogether with a halide. So find a way of converting an alkyl halide, an alcohol into an alkyl halide. Let's look at one way to make the OH group into a better leaving group. If we take an alcohol and react it with a reagent called para-toluene sulfonyl chloride, it's abbreviated PTSCl or TSCl, and has the structure shown here in the left box. In the presence of a base, pyridine, we can form a species called an alkyl tosylate. And an alkyl tosylate has an excellent leaving group. This whole group in a box is an excellent leaving group. It will fall off quite readily under both SN1 and SN2 conditions. Notice that the oxygen here in the alkyl tosylate is exactly the same oxygen that was present in our starting alcohol. The only thing that happened in this reaction is that we replaced a hydrogen with the sulfur-containing group to form the alkyl tosylate leaving group. The species that's being lost when an alcohol reacts with the para-toluene sulfonyl chloride molecule is a molecule of H and Cl, or hydrochloric acid. And that's the reason why we run this reaction in a solvent that is a good base, pyridine, is that the pyridine itself can react with the HCl and absorb it, causing the HCl to be consumed and to disappear in the reaction. So pyridine simply removes the HCl, which forms when an alcohol reacts with para-toluene sulfonyl chloride. This reaction has absolutely no effect on the stereochemistry at our carbon atom. If our carbon atom was cupped to the left, our carbon atom in our product would have the same cupping. If our carbon atom was an R chiral center, it would be an R chiral center in our product. So here is an example of making an OH group into a good leaving group by replacing the hydrogen of the alcohol with a sulfur atom of para-toluene sulfonyl chloride. And as a result, we make an excellent leaving group, which is the tosylate leaving group, often abbreviated OTS-, and this is one of the best leaving groups that exist. It's right up there in quality as iodine. A second approach to making an alcohol into a good leaving group would be to put a proton onto the oxygen atom. Once the oxygen atom receives a proton, we now have a much better leaving group, because when this carbon-oxygen bond is broken, we would make a water molecule. Water is a weak base, and so as a result, water is a better leaving group than hydroxide, OH-. And we can use a strong acid to encourage the OH group to fall off as a water molecule. And this occurs by forming the conjugate acid of our alcohol by putting a proton onto the oxygen of the alcohol functional group. Let's look how we can use that reaction to actually replace the OH group of an alcohol with the X with an X and form an alkyl halide as the product. So if we react a tertiary alcohol with HCl or with HBr or with HI, hydriodic acid, we can replace the OH group of the tertiary alcohol with the X group of our halogen. X equals chlorine, Cl, Br, or I. Now HCl and HBr are both stable acids. HI is not. And so we have to generate HI under the reaction conditions by taking potassium iodide, which is K plus I minus, and reacting it with phosphoric acid, which is really equivalent to H plus PO3 H2 minus. The I minus and the H plus can interact together and form HI under these reaction conditions, and the other product would be monopotassium dihydrogen phosphate. So we'll see that this is an SN1 mechanism, and it involves making the OH group into a good leaving group by protonating the oxygen, making it a water leaving group. So this is a good way to convert an alcohol into an alkyl halide. So let's look at the mechanism here. Got some extra information on here that shouldn't be here. We start off with an alcohol and we react it with a molecule of HX. One of the lone pairs on our oxygen of our alcohol can attack the HX molecule, breaking the HX bond to form the conjugate acid of our alcohol. And a molecule of X minus. Our conjugate acid now has as its leaving group a water molecule. We can simply break the carbon-oxygen bond and in the process make a carbocation. Our other product in this case is a molecule of water, and water is a much better leaving group than OH minus. Our carbocation will be the most stable when that carbon is a tertiary carbon atom. And that's the reason why this reaction only works for tertiary alcohols. Alcohols where we have 3 carbons attached to the carbon that has the OH group attached to it. Because those tertiary alcohols are going to form a more stable tertiary carbocation. Once the carbocation forms, then, we have X minus hanging around from the first step, and X minus can attack the carbocation, leading to the formation of a new carbon X bond in our product. And so this is a good way of converting a tertiary alcohol into a tertiary alkyl halide. And the mechanism is an SN1 mechanism because it proceeds by a carbocation intermediate. Well, we mentioned that another good way to get rid of an OH group is to actually replace it with a halogen. We saw it with tertiary alcohols in the previous slide, we can accomplish the same transformation for primary and secondary alcohols with different reagents. If we react a primary or secondary alcohol with the reagent shown in the box on the bottom of this slide, we can replace the OH group of the alcohol with our X atom. A primary alcohol will have one carbon attached to the carbon that has the OH group, and a secondary alcohol will have two carbons attached to that carbon. These particular reagents proceed by an SN2 mechanism. There's no carbocation intermediate, and as a result, we will be able to get optically active products from optically active alcohol starting materials. To replace the OH group with a chlorine atom, we can use basically four different sets of reaction conditions. One set of conditions are thionyl chloride and pyridine. SOCl2 its name is actually thionyl, THIONYL chloride. It was used as a chemical warfare agent in World War I, so it's a very nasty reagent. It will react with water violently to generate HCl gas, which is the reason why it was used as a mustard gas in World War I by the Germans. So the OH group in this case can be replaced with one of the chlorine atoms of the thionyl chloride molecule. Interestingly, this reaction actually can go by a retention, not inversion, at the carbon atom. And if you're interested in this reaction, you can read about it in the book. It's beyond the scope of our class. But you can get a retention of the product instead of an inversion. Well, the second condition is not just HCl, but HCl mixed with zinc chloride, which is a powerful Lewis acid. This reagent is called the Lucas reagent, and it will convert alcohols to the corresponding chloroalkanes, or in other words, alkyl chlorides. Another set of reagents that also work are phosphorus trichloride and phosphorus pentachloride. These are both very reactive molecules, react with moisture to release HCl gas. If we want to replace the OH group with a bromine atom, the best reagent for this is PBr3, phosphorus tribromide, and it will replace the OH group quite readily to form our alkyl bromide. Now, the full mechanisms of these reactions are outside of the scope of the class, but these are great ways of converting alcohols into alkyl halides so that now we can use the alkyl halides as substrates in an SN2 mechanism. The alcohol that we started with was a poor substrate for an SN2 reaction, but the alkyl halide products that we have are excellent substrates for an SN2 reaction. So in summary, if we want to do a substitution reaction, we can replace the OH group with a tosylate group, or alternatively, replace it with a halogen atom. Or finally, simply protonate the OH group and make it fall off as a water molecule. And that latter reaction only works for the SN1 mechanism. Well, we've simply, from this point back, used nucleophiles as if we could simply put them in a bottle. Very often in the laboratory we need to generate a nucleophile from another species. And one of the species that we're going to find quite conveniently is the conjugate acid of our nucleophile. Being the conjugate acid, it won't have a negative charge in its structure. As a result, the conjugate acid itself is going to be a weak nucleophile. We'd very much like to be able to convert that weak nucleophile into a good nucleophile where we have a negative charge present in the structure. And we can accomplish this by using a base to pull off the proton off of our nucleophile and to generate the nucleophile with its negative charge. And so our acid-base electron pushing is have the lone pair on the base, remove the proton, which breaks the hydrogen nucleophile bond, giving the pair of electrons and the negative charge to the nucleophile atom. So the nature of what base we use depends upon how acidic is that conjugate acid. We could use weak bases, or in some cases we need to use very strong bases. Depending upon how strong of a base we use, this will either be an equilibrium, where we have both the nucleophile and its conjugate acid being present, or we can drive the reaction to completion with a very strong base and have exclusively the anionic nucleophile being present. Let's look at how we could synthesize the nucleophile alkoxide from an alcohol. Alcohols are weak acids. Their pKa is about 15. And so one way to convert them into the alkoxide nucleophile is to react them with a reagent called sodium hydride. Sodium hydride structure is Na plus hydrogen with a pair of electrons and a negative charge. The H minus in sodium hydride is a very reactive molecule, an exceedingly strong base, and it can cleanly pull off a proton off of a large number of different molecules to generate a molecule of hydrogen. The hydrogen that's formed is a gas which evolves out of the reaction mixture. We use this particular base quite a bit in my research. As a result of the H minus pulling off a proton from our alcohol, we leave the oxygen with a negative charge and 3 lone pairs. And that conjugate base of the alcohol is called an alkoxide. It's an excellent nucleophile, but also quite a strong base. In addition to sodium hydride, we can actually use sodium metal in this reaction. The sodium metal reacts in an identical way with the alcohol to form a molecule of hydrogen plus the sodium salt of our alcohol, of our alkoxide. So we can use this reaction to make a good nucleophile, an alkoxide, from a poor nucleophile, an alcohol. Well, phenols are a type of alcohol that has the OH group directly attached to an arene ring. As a result of being attached to an arene ring, phenols are much more acidic than alcohols. Their pKa's tend to be around about 10, so they're stronger acids than alcohols. The conjugate base of a phenol is called a phenoxide, and it has a negative charge and 3 lone pairs on the oxygen atom. Because of the greater acidity of a phenol, we can use a much weaker base, sodium hydroxide, to pull off the proton. And in doing so, we convert what is a weak nucleophile with 2 lone pairs on the oxygen into an excellent nucleophile with a negative charge on the oxygen atom. So this is a very strong, this is a very good nucleophile. Sodium hydride can also be used in this reaction, and sodium metal, but they're both overkill compared to using just regular sodium hydroxide. Here's an example of a synthesis from the research that I do with the Alzheimer's Institute here on campus. We take this starting material, which is a phenol called vanillin, and we pull off a proton from the OH group to generate O-. Now, the molecule vanillin has a lot of other functional groups on its structure. It has an aldehyde group, and it has an ether group adjacent to the OH group. Vanillin is the active flavorant in both artificial and natural vanillin. vanilla. As a result of the various substituents on this ring, we have found that the O- is a fairly weak nucleophile. I can show students why it is a very weak nucleophile, but we have just found that it is an exceedingly weak nucleophile. And we've had trouble with the adjacent OCH3 group blocking the reaction of the nucleophile with an electrophile. As part of our research, we want to synthesize molecules that have an amine attached off of the oxygen that was once the phenol. And we do this by taking this particular alkylating agent, which is our electrophile. It's a primary alkyl chloride. Note that chloride is a very poor leaving group, and yet this is the way that the molecule is sold commercially. In running this reaction, we find low to moderate yields of the ether product, where we've now made a carbon-oxygen-carbon bond from what was once a phenol. So this is used in the synthesis of Curie-like derivatives in my research group. Let's look at another kind of nucleophile that we can synthesize in the laboratory. Got a big error on this slide. We start with a molecule that has an SH group in its structure. This is a thiol. It has the thiol functional group. We can react that thiol with a strong base. Sodium hydride is a very powerful base. We could also just use sodium hydroxide. And we can pull off the hydrogen from the thiol to generate conjugate base of the thiol, which is called a thiolate. Being negatively charged, the thiolate is one of the weak bases but good nucleophiles that we learned about in part 1 of this 3-part series. So by reacting with sodium hydroxide, we can make a molecule of water and the thiolate molecule. With sodium hydride, we can make hydrogen gas, H2, and our thiolate. We can also use sodium metal, but both sodium hydride and sodium metal are overkill because the pKa of a thiol is right around about 9 as a pKa value. So it's actually fairly acidic, and we don't need to use very strong bases to pull off the proton. Well, another type of nucleophile that we saw early in the first part of this 3-part series was something called an acetylide anion. It had a negative charge on an sp hybridized carbon that's part of a carbon-carbon triple bond. This acetylide anion is a very strong base, but it will react in substitution reactions with primary alkyl halides. We can make this acetylide anion in the laboratory by reacting an alkyne that is at the end of the molecule chain, so that it has a hydrogen on one end of the carbon-carbon triple bond, and react this with a strong base. This strong base is sodium plus NH2 minus. Since nitrogen is a weakly electronegative atom, the NH2 minus can remove the proton quite readily, leaving the lone pair a negative charge on our carbon atom and forming a molecule of ammonia. So this is an excellent way of making the acetylide anion from an alkyne that's at the end of the chain. We're going to see more about this reaction in Chem 314. In this particular case, we have a carbon being our nucleophile. Well, one family of reactions that unfortunately we're not going to be able to spend much time with in Chem 314 are nucleophiles that we can make from ketones, aldehydes, and related molecules. If we have a ketone or an aldehyde where we have a carbonyl group, The carbon attached to it is referred to as an alpha carbon, and the hydrogens on that alpha carbon are quite acidic. And so it's possible using a strong base like sodium hydride to pull off one of those three hydrogens of our methyl group and to leave a negative charge and a lone pair on that carbon atom. The other product of this reaction is a molecule of hydrogen. This conjugate base of our aldehyde or ketone is resonance stabilized. We can push the electrons down between the two carbon atoms and at the same time push the carbon-oxygen double bond up to the oxygen atom. And as a result, we have a second structure that we can draw for this conjugate base that puts the negative charge on the oxygen atom, and we have a carbon-carbon double bond. Well, species like these are called enolates because they have an alkene, En meaning a double bond between carbon atoms, and olate meaning we have an oxygen that has a negative charge on it, often written as ate, as in sulfate. We have an enolate as being the name of this molecule. And it's quite nucleophilic at both the carbon atom and the oxygen, and depending upon our reaction conditions, it will react with an electrophile, an alkyl halide, at either or both of those two positions. Here's an example of an enolate alkylation. In this molecule, we have two ketones. The presence of both ketones cause the carbon between them to be quite acidic. It's alpha to both carbon-oxygen double bonds, and as a result, the two hydrogens on that CH2 group are very acidic. They can be removed with as weak of a base as sodium hydroxide to form a negative charge on the carbon atom. And we can draw resonance structures that push the electrons to the left or to the right and up to the two oxygen atoms. So there are a total of 3 resonance structures for this anion, this conjugate base. As a result, it's an exceedingly stable conjugate base. Being stable, though, it can react with an electrophile, and in this case we can react it with iodomethane, which has a carbon atom that's really quite electrophilic, and in the process put a new carbon atom into the molecule. And so we form a carbon-carbon single bond in our structure. So we won't spend time on this in class, but in more advanced treatments of organic chemistry, you would be taught a whole wealth of chemistry that can result from the ability of making carbon-carbon bonds through alkylation of an enolate. Alkylation meaning reacting an alkyl halide with the enolate to put the alkyl group onto what was once a negatively charged carbon.